In this section, we talk about the amelioration of approximate solutions to p-adic equations. The word amelioration means improvement. Recall that in the previous section, we have established propositions on the existence of solutions to p-adic equations given the existence of solutions in an for all n, where an means z mod p and z. So a natural question is, what if we do not know the solutions in an for all n? Or equivalently, we do not know the solutions to the p-adic equations modulo pn for all n, but only for some n. In this case, in general, we do not expect to get a precise solution in Zp, the ring of p-adic integers. But as a compromise, can we get an approximate solution instead? And this is a question that we plan to answer in this section. The first task in this section is to establish a lemma that can be viewed as a p-adic version of Newton's method. Let f be a polynomial in one variable over the ring of p-adic integers, and let f prime be its formal derivative. Let little x be in Zp, and we take two integers n and k, such that k is non-negative and is less than half of n, and that f of x is congruent to 0 modulo Pn, and that the p-adic valuation of f prime of little x is equal to k. Suppose f, little x, n, and k satisfy these relations. In particular, this statement means little x is a solution to f modulo Pn. And as an analog to the Newton's method, we're going to move one step further from this little x. From here, we can further get a solution to f modulo Pn plus 1. Formally, we have there exists a y in Zp such that the following three statements hold. First, as I said, y is a solution to f modulo Pn plus 1. One step further from here. And second, the p-adic evaluation of f prime of y is still equal to k. And thirdly, y is associated to x in the relation that y is congruent to x modulo p to the power n minus k. So this is our p-adic Newton's method lemma. Now let's prove this. The core part in the proof is the construction of this y. And in view of the third statement we want to prove, we are going to construct y as follows. we take y of the form x plus p to the power n minus k times z, where this little z is in zp. Then we immediately have number 3. Now our goal becomes, how do we smartly choose this z such that this y will satisfy number 1 and number 2. And to this end, we are going to use the idea of Taylor expansion. We'll take advantage of this construction that y is x plus something. And we will do a Taylor expansion around x with radius this much. And to this end, we're going to write and prove a sublemma, which states that R be any ring, and F be a polynomial over R. And we choose two elements, R0 and R, in this capital R. Then we have the following expansion. F of R plus R0 is equal to F R0 plus F prime of R0 times R plus A times R squared for some A in R. And now let's prove this sublemma. Suppose F takes the following form. Then F of R plus R0. And now we're going to apply the binomial theorem to individual segments. And we single out the highest and second highest powers of R0. This is the sum of the highest powers of R0. R0 to the power j for j equals 0 and n. And then we sum up for j equal to 0 to n for the second highest powers of R0, meaning R0 to the power j minus 1 times R. So this is the second term. And for the rest, by the binomial theorem, they must be something times R squared, because we have already pulled out all the terms with R to the 0th power and R to the 1st power. So the rest will be something times R squared for some little a in R. And from here, we see that the first term is precisely f of R0. And for the second term, if you look at this part, this part is precisely f prime of R0, followed by an R. And this is precisely what we want to prove. In our case, we are going to take this R0 to be x, and this R to be this part, p to the power n minus k times z. And it follows from this sublemma that we have f of y is x plus p to the power n minus k times z equal to f of x plus r, which is p to the power n minus k times f prime of x. And the last part is some a times r squared. And r squared is p to the power 2n minus 2k times z squared. And now, for simplicity, we're going to combine this a with z squared. So let me erase this z squared. And this is just true for sum a in ZP. ZP is our ring. And this a is something more than just this a, but for sum a. So this is always true. And we are going to put an asterisk for this equations label. Now, let us review our assumptions for f. In our assumptions, f satisfies this. First, f of x is congruent to 0 modulo Pn. That means f of x is equal to some p to the power n times b for some b in Zp. This corresponds to this assumption. And we have yet another assumption, saying that the p-adic valuation of f prime of x is equal to k. And that translates by definition to the following. F prime of x is equal to p to the power k times c. And this c is not just an arbitrary element in Zp, but an invertible element in Zp. So starting in this video, I'm going to use a better notation for our previous U, the subgroup of invertible elements in Zp. I'm going to put an extra bar here to make this U more special. So this U is a vertical line, is our previous U. I'm just trying to make this U less generic. So this means C is invertible. And that is a precise definition for the p-adic valuation of f prime of x. Remember, as I said from the beginning, our goal is to construct this y satisfying 1, 2, 3. And we take y of this form. So now the goal is to carefully construct this z. And now, with this, we can construct this little z from b and c. What we're going to do now is we're going to make z to be an element in Zp, satisfying that b plus zc is 0. And this is possible because c is invertible. So we can choose z such that b plus z times c is equal to 0 in Zp. And in particular, if you look at this equation, modulo p, you can write this as b plus z times c congruent to 0 modulo p. And you will see why we are doing so in the next step. And from here, together with this equation with asterisk, we have f of y is equal to Pnb plus Pn minus k z. And we plug in this f prime here. This is pkc plus p to the power 2n minus 2k times a. And now we're going to combine the first and second terms by pulling out p to the power n. And the rest is b plus zc. As the last term, p2n minus 2k times a. Now we claim that this guy will be congruent to 0 modulo Pn plus 1 as desired. Why is that? First of all, because b plus zc is congruent to 0 modulo p. So this part is divisible by p. And together with this part, the whole term is divisible by Pn plus 1. And now for the second term, we're going to use our assumption. Our assumption says that n is strictly bigger than 2k. So 2n minus 2k must be at least n plus 1, because n is strictly bigger than 2k. So 2n minus 2k must be at least n plus 1. So this part is divisible by p to the power n plus 1. So the whole thing is divisible by Pn plus 1. This is by our assumption. N is strictly bigger than 2k. And this part is because of this. So the whole thing is congruent to 0 modulo Pn plus 1. And this verifies this, our statement number 1. Finally, we're going to verify the statement number 2, which says that f prime of y also has the p-adic valuation equal to k. To this end, we replace f in the statement with asterisk by f prime. So we have, in this case, f prime of y equal to f prime of x plus still Pn minus k times z. And now this part will become f double prime, meaning the second derivative of x. And the last part is the same. And clearly, these two terms are both divisible by p to the power n minus k. So this is congruent to f prime of x modulo p to the power n minus k. And what is f prime of x? F prime of x is p to the power k times c. Now here is the subtlety. Although we already know that C is invertible. We do not know whether f prime of y is equal to p to the power k times c in Zp. We only know that they are congruent to each other modulo p to the power n minus k. So, is it possible for us to show that f prime of y has the form that p to the power k times some invertible element which is not necessarily c, so that we can conclude that the p-adic valuation of this guy is equal to k? And the answer is yes. The key here is that n is bigger than 2k. Or in other words, n minus k is bigger than k. What does that mean? That means p to the power k is a smaller power than this. And p to the power k must divide f prime of y minus p to the power k times c. But because p to the power k already divides this part, so this means p to the power k divides f prime of y. And therefore, f prime of y is equal to p to the power k times c prime for some c prime, not necessarily invertible at this moment, but it is in Zp, because p to the power k divides f prime of y. And now again, by this relation, we must have p to the power n minus k divides p to the power k times c prime minus this guy. And if we cancel p to the power k from both sides, we have that p to the power n minus 2k divides c prime minus c. Again, we have here implicitly used the fact that n is strictly bigger than 2k. And this implies, because n is strictly bigger than 2k, p divides c prime minus c. But we already know that this c in our construction is in U, meaning it is invertible. And it is invertible if and only if it is not divisible by p. So it follows that c prime cannot be divisible by p as well. So c prime is invertible. And therefore, f prime of y can be written as p to the power k times c prime for some c prime, not just any element in Zp, but actually an invertible element. And that by definition means f prime of y has p-adic valuation k. In case some of you may not remember why we are allowed to cancel p to the power k from both sides, that is because the multiplication by p to the power k is injective. And that injectivity follows from proposition 1 on page 11 of Sarah's book. We already used this property several times in our proofs, but just in case you don't remember, okay, this follows from proposition 1, page 11 of Sarah's book. And this verifies this, the number 2 of 3 statements we want to prove. So we have verified all of them. And this completes the proof.